The gaseous state. There may be ideal gas, there may be real gases. The ideal gases are the one which follow Boyle's and Charles' law at all temperatures and pressures. For an ideal gas, the gas equation is PV is equal to nRT, where n is number of moles. If the same equation is to be followed by real gases, that is, the gas is normally present, or the gases to which we deal normally, there is a pressure correction and also a volume correction. Pressure correction becomes P plus A upon V square, whereas volume correction becomes P minus P, that again becomes equal to nRT. This equation, P plus A upon V square into V minus P is equal to nRT, is also known as van der Waals equation, where A and B are van der Waals constant for specific gases. Every gas will have, all the gases following van der Waals equation will have their specific van der Waals constants A and B. R is the gas constant, which is again a universal constant. A ratio PV is to RT, gives the number of moles. For 1 mole of ideal gas, PV upon RT, that is compressibility factor, that comes to be equal to 1. Z is the compressibility factor, which is equal to 1 for 1 mole of an ideal gas. The value of compressibility factor deviates from 1 for if the same is to be calculated for real gases. Thus, the compressibility factor for real gases deviates from 1. Compressibility factor equal to 1 exhibits the closeness of the behavior of a real gas towards ideal, the comparison of a behavior of real gases towards ideality. The compressibility factor, that is the dashed line, that is equal to 1 for an ideal gas, whereas it is varying from the value of 1 in case of real gas. If we consider a single real gas, its behavior at different temperatures and pressures, and the compressibility factor is plotted against pressure, we get at higher temperature, that is 400 Kelvin, the behavior of gas approaches the ideal behavior. That is, the pressure is very low and the temperature is high. That is, the volume is very high. Consider another line, the blue line. The ideal behavior is being exhibited at a value approximately 230 atmospheric pressure. In case of green line, the ideal behavior is being exhibited at a value of 270 or 280 atmospheric pressure. Thus, when the volume is high and the temperature is very high, whereas the pressure is low, the real gases behave ideally or approaches the ideal behavior. Let us consider a pressure volume isotherm of a specific gas. The compound exists in gaseous state at very low pressures. It exists in the liquid state and it exists in the solid state at a very high pressure. Let us consider the lowermost isotherm. The gaseous state, the volume decreases and the compression starts and the liquefaction of the gas starts at T, approaches C, B, the pressure again decreases, but the liquid state still exists. So the dashed line CBA exhibits the anomalous behavior of the compound GCBA and F dash and F. In this region, the compound exhibits anomalous behavior. The region in which it exists in the liquid state, it is GCBAF. Its a behavior towards temperature and pressure is anomalous. Take another isotherm of this of the very same gas, but at a higher temperature. The region of anomalous behavior is GCBAF. In the region GCBAF, it also exists in the liquid state. The gas starts getting compressed, approaches the G, liquefaction starts, and continues till point F. And at F, the solidification starts, and the pressure becomes constant. Pressure increases while the volume becomes constant, and from F to higher values of P. Consider one more isotherm, that is the red curve, gaseous state, gaseous state, gaseous state, no liquefaction, again the gaseous state. This region is the region in which the compound exists in the gaseous state. So at a particular isotherm, there is a point C, that is a critical point at which, however high the pressure we are going to apply, the gas will not convert into the liquid state. There is another point C on another isotherm. On further isotherms, we won't get the point C, instead we'll get the point C will vanish, that is the critical point will vanish. So critical point at a particular isotherm at a particular temperature Tc is at this we'll get Vc, at this we'll get Pc for this isotherm. Another point will get Vc and Pc for another isotherm, and likewise we can join different points of different critical points at different isotherms to get a region in which the liquid state can exist. Gas at a critical point has pressure Pc, volume Vc, and temperature Tc. These are various isotherms for which we have obtained different critical points. The van der Waals equation for real gases is a correction in pressure and volume in the ideal gas equation, the pressure correction and the volume correction. P plus A upon V square, V minus P into V minus P is equal to nRT. Finally, on solving it, we get this equation. Comparing this equation to a cubic equation, V minus Vc, we get this. Comparing the coefficients of Vq, V square and V, we get these values, and on solving them, we get the value of Vc, Pc, and Tc in terms of variables A and B, where A and B are van der Waals constant Every gas obeying van der Waals equation will have its specific van der Waals constant A and B. R is the gas constant. From the values of A, B, VC, PC, and TC, we can get the conditions, we can get the parameters for critical state. Another slide exhibiting a plot between compressibility factor and the pressure. The ideal behavior shows the compressibility factor equals to 1. The air, which is a composition of several gases, the ideal conditions are approached at very low pressures and high temperature when the volume is very high.